we have already covered logistic regression and linear regression. We understand that in logistic regression, there is a classification task that we are trying to achieve. And in the linear regression, we're trying to just predict what is the next precise score that on a continuous feature. Before we go to the next uh, machine learning model, which is nothing but our decision tree, I wanted to give some intuition towards measures of impurity, which is basically the backbone of decision tree. And decision tree can be applied both on classification and regression problems. Okay, it is the same concept, but if you want to go and apply a classification thing, you go and use a decision tree classifier, and if it is a regression problem, we use a decision tree regressor. Let us see what is impurity first of all. So impurity is nothing but when we consider a data set, and in, let us say, for now, let us consider that we have a classification task, and in the target column, we have two classes. Uh, there is class 1 and class 0. What you see on the right side is something like a classification problem where we have stars and circles. Now, when we have one feature which is having couple of records with stars and couple of records with circles, that is highly impure. And we want to segregate, we want to achieve some kind of a classification, right? We want to segregate all the stars in one category and all the circles in one category. So how do we do that? So in order to do that, what decision tree does is it measures the impurity by doing some calculations based on Gini index and entropy. Okay, so Gini index and entropy is nothing but it is a way to see how much impurity is present in that feature. Say if I have all the features belonging to single class, then there is no impurity at all. So I should get some way to calculate that the impurity in this case is 0. On the other hand, if we have something like this, couple of stars and couple of circles, we should have a non-zero value. Okay. So to do that, we have two things, as I told, Gini index and entropy. Okay. Gini index and entropy are just calculating how much impure the data set is. So first look at Gini index. Gini index is nothing but it is following this formula wherein we calculate 1 minus a probability of each class. Say for example, if I have half of the values of class 1 and half of the values of class 0, then the probability of class 1 is 0.5 and the probability of class 0 is 0.5, and I can achieve the Gini index is 0.5. Okay. On the other hand, if I get all the classes as only one, there is only one class in the feature, then the probability for getting the class is 1, and hence the value will be 0. This is how it is measuring the impurity. Takeaway is that whenever there are more than one classes in the feature, you will have a non-zero value. If there is only one class within the feature, then you will have a 0 value. This is a Gini index formula. Similarly, entropy is a little more to it. We just have, instead of doing a square, we are trying to also consider the logarithmic value. So it is calculated by using this formula, minus p probability into log of probability. So same case, like let us say that we have two classes and class 1 is half and class 0 is half. Then for that, the entropy would be calculated as 1. And given a case that there is only one class in the feature, then the entropy will be 0. Okay, this is how it looks like. But anyway, let us see how we can apply on a data set and find out how this entropy or Gini index is being used. Okay, we did not cover decision trees, but what happens in a decision tree is it looks to go with a greedy approach. When I say greedy approach, it tends to find out where there is more information gain. Based on that, it will try to differentiate or it will try to form subsets from a given feature, and then it will try to grow a tree. Generally, what happens in a nutshell, I'm not going to explain about decision tree now, but what generally happens is you start off with one feature. you start off with one feature, and from that feature, we'll see what are the different values that are present here. Let us say you have one more column like this and like this. Okay. This is my age. I'll say age less than 50, age greater than 50 and ranging till 60, and age greater than 60, like this. And under age, maybe I can have gender, male and female. Here also you'll have gender, male and female. Here also you'll have gender, male and female. And after gender, maybe you can have salary slab, and it will continue to grow the tree. This is a tree in reverse. Like if you notice a tree, it would be look like this, right? This is a tree in reverse. That is why it is called as a decision tree. And it is trying to execute some decisions at each node. It is trying to check, is my age less than 50? Is my age between 50 and 60? Is my age greater than 60? But what makes decision tree to choose age as the first column? Why not choose gender as the first column? Or why not choose salary as the first column? This all depends upon information gain. That is why it is called as a greedy approach. Whichever column gives us more amount of information, that would be the column for making the first split. Okay, so we understand now. We will look at what is information gain. Information gain is nothing but the entropy difference at the target and the weighted average entropy of a given feature. Okay, so let us say if we have 4 columns and one of them is a target column, we'll calculate the entropy at the target and we'll find out the weighted entropy of each feature, and then we'll see which feature is having most information gain. Based on that, we'll try to make the decision tree to follow. Now, let us say, keeping this in mind, let us take a simple data set and address this and find out which feature is giving us more amount of information gain. Let us say that this is one small data set wherein we have couple of features. We have outlook, we have temperature, we have humidity, windy, and this is our target play. Whether I'm going to play or not based on the given conditions of outlook, temperature, humidity, and windy. Given a case that I don't know anything, I'm not going to look at entropy. I'm not going to look at information gain. I'm not going to calculate all the measures of impurity and all. If I make a decision tree to go and look at it, probably we will have something like this. First, I will look at temperature. Randomly, I'm choosing one column. I'll look at temperature. If I see temperature, what are the different values that I have? Say, for example, this is my data set, the same data set. I look at temperature. I have 3 different columns. Three different values: cool, hot, and mild. That is what you see: cool, hot, and mild. Hot, I have 4 records. Mild, I have 6 records. Cool, I have 4 records. Okay, let us take one value. For now, I'll take hot. Okay, as I said, I have 4 records. In hot, I see 2 of them are having no play and 2 of them are having play. Now, what is the next feature that I want to split? For now, let us say in this diagram, I have taken outlook. So I have taken outlook. So if it is sunny, I'm not going to play. If it is overcast, I'm going to play. Okay, that is what the figure says. When the temperature is hot, look at the outlook. If the outlook is overcast, go and play. If the outlook is sunny, don't play. Similarly, if you go and check at mild, so let us go and choose mild. In mild, I have taken humidity as the next column. So again, if I see mild, my target column is still having some impurity. So to resolve this, I'm going to take humidity as one of the feature for further splitting. So in humidity, I have 2 features. Sorry, 2 values. One is high and normal. So high and normal. What if the value is high? Again in high, I have furthermore. Still the impurity is there. After high, I'm going to choose windy. Again in windy, I have two more values, true and false. Like that, the decision tree is going to make. So if you do not find out the information gain, your tree is gonna get bigger and bigger. When I say bigger and bigger, obviously it is gonna be compute intensive. It is gonna be slow, which we don't want. So what decision tree does is it uses information gain as one of the criteria to find out what is the best column to start with. So how to calculate entropy and information gain? That is what we are trying to learn in this video. So first we'll go and calculate what is the entropy at the target level. So what is the target I have? Play is my target. And as you know, I have 14 records. Out of this 14, I can go and play for 9 times. So the probability without considering any of the other factors is 9 by 14, correct? So probability of playing is 9 by 14 and probability of not playing is 5 by 14, as simple as that. So entropy, I'll go and calculate by applying the same formula, probability into log of probability. So probability of not playing 5 by 14 into log of 5 by 14 minus 9 by 14 into log of 9 by 14. So I'm getting the calculation as 0.9403. I don't want to go in deep. Like if you want to go and calculate, you can apply this formula. Maybe you can use a calculator or Excel. You can get these values and you'll achieve to 9403. Okay. Now, when I want to calculate entropy of a feature, I want to consider the weighted one because I don't want I want the decision tree to make conclusions based on the target column. I want to split looking at the target column, keeping the target column in mind. So what I'll do is I'll try to take one feature now. Let us say that I take temperature. Okay, in temperature, let me clear this filters for now. 1 minute. Okay, in temperature, as you notice, I have 3 different values. Okay, now let us take one value at a time. Let us take cool for now. In this cool, I have 4 records, out of which there are 3 yes and 1 no. Okay, so what would happen is if I go and take cool, I calculate the probability of going to play given that it is cool. So the probability is 3 by 4. Given that it is already cool, my probability will change 3 by 4 into log 3 by 4 minus 1 by 4 into log 1 by 4. Okay, this is same entropy formula, but because I want to give weightage to the target column, I'm going to calculate given it is cool, given it is mild, given it is hot. Then I get these values 1, 0.9183, 0.8113. The weighted entropy would become what is the probability of hot. So I have 4 records out of 14. The probability is 4 by 14. 4 by 14 into 1. Similarly, 6 by 14 into 0.91 and 4 by 14 into 8113. So the weighted entropy for temperature would become 0.911. Okay, this is how you calculate weighted entropy. Now, what is the information gain? You calculate the entropy of target, which is 9403, and weighted entropy of temperature, which is 9111. And you get the information gain as 0.0292. Okay. Take a minute, you can pause the video, look back at the calculations of what I said. There is only one thing. One is entropy and one is weighted entropy. Weighted entropy is considering the target column. If you don't consider the weighted entropy, then you will be going at information content, which we'll talk about later. But for now, we have to consider the weighted entropy and entropy at the target so that we can calculate the information gain. Similarly, you can apply the same logic to look at what is the information gain considering outlook as a feature, and what is the information gain considering humidity as a feature, and what is the information gain considering windy as a feature. After applying all the calculations, you arrive that outlook is the best feature to start with, followed by humidity, followed by windy, followed by temperature. So let us say if I start with outlook, I go and check at my leaf nodes. If I'm able to completely achieve a zero, what you call zero impurity. If zero impurity is not present, then I go to the humidity. With humidity, if I achieve zero impurity, I'm good. If with humidity also, if you're unable to achieve, then go with windy. Okay, and so on. So I'll show you how the decision tree looks like now. So when I consider outlook, just remember this, okay? Outlook followed by humidity. So when I consider outlook, I look at if it is overcast, I get a complete pure data set. Okay. If it is rainy, it is impure. Why it is impure? Let us go back to the Excel. I'll say if it is overcast, I'm going to play. It's completely pure. If it is not overcast, let us say if it is sunny. Now it is impure. I have 3 records of no and 2 records of yes. As per the information gain, what is my next column? My next column is humidity. Now you notice if the humidity is high, I get a complete pure data set. All of them belonging to class 0. If the humidity is normal, again I get a complete normal data set. There is no impurity at all belonging to class 1. That is what the decision tree is also saying. Suppose I'm going to start with outlook. If my value is sunny, I'm going to check my humidity. If the humidity is high, don't play. If the humidity is normal, go and play. Similarly, the same thing with rainy. Okay, let us do the same exercise one more time. Let me remove humidity here. I'm going to choose rainy. In rainy, again, my data set is impure. Again, as per the information gain, my next column should be humidity. So in humidity, I'm going to choose whether my humidity is high or not. So if it is high, again my data set is impure. So what I'm going to do next, I'm going to choose windy. Windy, if it is true, don't play. If it is false, go and play. Like this. So that is what it is saying. Check at humidity. You're getting an impure data set. Next column would be windy. If the windy is false, play. If the windy is not windy is true, play. Not play. Similarly, if it is the humidity is normal, and if it is windy, no play. If it is not windy, go and play. That is how you get a smaller decision tree as compared to a random decision. Like if I make random columns, like in this case, this decision tree is quite big and more complex. Okay, but if you go with the information gain approach, it becomes more simpler and precise. When it is simpler, it is more fast. Okay, that is why it follows a greedy approach. The decision trees are greedy approach. We are going to cover decision tree in the next session, but for now, let us stick to information gain and measures of impurity. Okay, now you understood what is entropy, what is Gini index, what is information gain, and there are 2 other things which we will have to look at. One is the information content and ratio. Just as I mentioned, if you do not consider the target column, entropy of a given column would be the information content. Like I'm not looking at what is my target column. I'm just looking at, for example, if I look at outlook. So if I let me go and remove all of this. Yeah. So if I look at just outlook, I'm not going to look at any of these columns. Only at outlook, there are about 14 values, out of which I have sunny 5 records and rainy another 5 records, outlook 4 records. Okay, so that is why you will have for sunny 5 by 14, rainy 5 by 14, outlook 4 by 14. The probability of sunny, probability of rainy, probability of outlook. That is how you go and calculate the information content as 0.47. And the information ratio is nothing but the information gain for that feature divided by information content of that feature, which is 0.5196. We will generally stick to entropy because entropy is much better than Gini index. But in some cases, maybe Gini index can also outperform. But by default, it would go with entropy. Okay, this is what the measures of impurity is. we will use this impurity, measures of impurity, in the next session when we learn about decision tree. Okay, that's all for today's video. Thank you so much.